Okay, ladies and gentlemen, so in this video what we're going to be looking at is using information from net forces and our new understanding of friction to solve problems. So this is a very basic problem dealing with friction. So I'm going to walk us through actually going about solving this problem. And then later on you will have more practice to do. So first, let's read the problem. A block is pulled along a horizontal tabletop at a constant speed by a force F. The mass of the block is 10 kilograms and the coefficient of kinetic friction, or mu k, between the block and the table is 0.3. Okay, here's a picture. Draw a free body diagram of the block on the dot below. Okay, so there's some important information in this problem. First of all, the word constant speed is very important because that implies that the net force on our object is equal to 0. Remember, in order to accelerate, or if we're accelerating, then we would have a net force. But if we're not accelerating, if we have a constant speed, then our net force is 0. Okay. And additional information we have about this problem: the mass of the block that is being pulled is 10 kilograms. Coefficient of friction is 0.3. So then here is a picture. Again, we're looking at the block, so the block is our system. And we're looking at forces that are acting on our system. So if we draw a free body diagram of the block, we would say, well, agents that are being acting on my system would be the Earth, and the Earth would apply a weight force or a gravitational force downward. We have the floor, and the floor would apply a force upward and perpendicular to itself, or a normal force. We have this general applied force, which has been labeled F, and we have a frictional force, which is opposing this applied force in the opposite direction of motion, or our force of friction. Great, so here's our free body diagram. Since we're moving at a constant speed and our net force is 0, we would expect the up and the down to be the same length. We would expect the left and the right to be the same length. I'm not sure how I did on that, but that's what I would expect. I know that my net force from this is 0. I know that my net force then in the x direction has to be 0, or in the horizontal direction has to be 0. I know the net force in the y direction, or the vertical direction, has to be 0. And we're going to say this way is my positive direction, and we're going to say this way is my positive direction, just for ease sake at this point. Okay, so let's keep moving down our problem. So then one of the things we should be able to do from this is first off calculate the magnitude of the normal force on the block. Well, the normal force lies in our vertical plane, or along our y-axis of our coordinate axes. So then we're going to say, well, I know that the sum of the forces in the y direction is going to be my normal force minus my gravitational force. And normal is up, gravitational is down, so it would be plus negative gravitational force gives me this. I also know that the sum of my forces in the y direction equals 0. Because of that then, the magnitude of the normal force has to be the same as the magnitude of the gravitational force. Well, we know a way to calculate the gravitational force on any planet. Specifically in this case we're looking at Earth, and we're going to take the mass times the gravitational field strength on Earth, which gives us 10 kilograms times 9.8 newtons per kilogram. And the force of gravity, or the weight of this object on Earth then, is 98 newtons. So then in this case we know that the magnitude of our normal force is 98 newtons. And that's the setup for that. Okay. Then the next question says calculate the magnitude of the force F required to pull the block. So then looking back at our free body diagram, we know that this force F is in the horizontal, or in the x direction. And the sum of our forces in the x direction then must be in our x direction. So we have F is our positive direction plus a negative force of friction. And we also know that the sum of the forces in the x direction has to equal 0. So then, with that being the case, we know that our force F has to equal our frictional force in magnitude. Okay, well we again have a way to calculate frictional force, and if we take the coefficient of friction times the normal force, we can obtain our frictional force magnitude. So our frictional force then is our coefficient of friction, which we saw at the top was 0.3, times our normal force, which we just calculated for in the last part of the problem, 98 newtons, which means our frictional force is equal to 29.4 newtons, which means that the force applied to this object is 29.4 newtons. Okay. And the last part of our question, calculate the acceleration of the block when the magnitude of the pulling force F is 50 newtons. Okay, so then the only thing that's changed about this scenario, I haven't changed the gravitational force, I haven't changed the normal force, I haven't even changed the frictional force, because I haven't changed the mass, I haven't changed my normal force because in this case they're equal, and I haven't changed my frictional force because I haven't changed the surfaces, and I haven't changed how much they're pushing against each other. So then the only thing I've changed is this pulling force. And now if I want to calculate an acceleration, I'm going to use Newton's second law, which says that an acceleration on an object can be determined by taking the net force on the object and dividing by the mass. Specifically in this case, I'm looking for the acceleration in the x direction, because the x direction is the only direction in which I have a net force. So the acceleration of the object is equal to my force minus my frictional force divided by my mass. My force then now is 50 newtons. My frictional force, which we found up here and stays the same, is 29.4 newtons. And the mass of the object, as it said at the top, was 10 kilograms. So then the acceleration of the block with that force is 2.06 meters per second squared. Okay, and using that acceleration we could determine how far an object traveled in a specific amount of time, or how much time it took to reach a specific velocity, etc., 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 given more information. Okay, so again, to review. First, we're reading the problem, looking at a picture or drawing a picture if there isn't one, determining our system, drawing a free body diagram, determining maybe what our net force equations may look like if they're zero, using our net force equations to solve for things like a normal force or an applied force in this case, knowing that our gravitational force is mass times the gravitational field strength, knowing that our frictional force is a coefficient of friction and a normal force, and applying all of that information together to solve for an acceleration using Newton's second law of motion. Please feel free to review this problem as you go through. Otherwise, good luck.